All right. So again, we started off, you're looking at the mean value theorem and kind of different scenarios with it. So again, the process that you've been duplicating throughout this exploration is looking at the secant lines. Sorry, the secant line, and if there are any tangent lines that are parallel to it. So this first one we went through together. So we've got our 2 points here, and drawing the secant line through it. And it said to then draw the tangent line that is parallel to it. They tell us that somewhere between 3 and 7, there is a tangent parallel to the secant. Alright, so I think we said somewhere around here. And that occurred at around 5.5. So then it asks you about whether or not your function is differentiable and continuous. Now notice it's asking about differentiability on the open interval. We're not including those endpoints. We don't really care about them for differentiability. Continuity, though, it is including those endpoints. So keep that in mind. All right. What does that mean to be differentiable? Yeah, you can take the derivative everywhere within there. So if I look at this part of my graph, from 3 to 7. Can I take the derivative everywhere within there? Yeah. And another way that we can think of this, go ahead and write this on your paper. The differentiable function is smooth and continuous. So what I mean by that is smooth, there's no sharp points, so no corners or cusps. And continuous, there's no jumps within there. Remember, a function must be continuous in order to be differentiable. The other thing you have to be aware of is vertical tangents would cause it to not be differentiable. So you'll hear me say smooth and continuous or smooth and connected curve. So this is indeed differentiable on that open interval. Is it continuous on the closed interval and including those endpoints? Yeah, I can trace it with my pen without picking it up. Alright, so we see here that our function is both differentiable on the open, continuous on the closed, and it has a place somewhere within that interval where the tangent line is parallel. Keep that in mind. Alright, so now our next piece, same function, but now they're having us look at the interval from 1 to 7. Alright, so again, drawing the secant line. And they tell us that there are actually 2 values within this interval where we have that tangent line parallel. So we can see probably about here somewhere. And then, what were those 2 approximate values you guys found where it occurred? I agree, about 2.5 and 5.5. Again, yours might be a little bit different, but if you had 4, that's incorrect. So about 2.5 and 5.5 is the x value on that interval where those tangent lines occur. All right, is our function differentiable on that open interval 1 to 7? Yep. And is it continuous on the open interval? Yes. So again, notice we have it's differentiable on the open, continuous on the closed, and we have actually 2 times in which the tangent line is parallel. All right, so now let's take a look at a funky looking one. This is an actual equation. They gave it to us here. And it says draw a secant line through the point 1 with its y value and 5. Alright. Is my function differentiable on that open interval 1 to 5? Why not? Right, we have this cusp right here. So there is a point that it's not differentiable, so we can't say it's differentiable on the whole interval. So that causes an issue for us. Is our function continuous on the closed, though? Yeah. Again, I can still trace it starting at one endpoint, going to the other without picking up my pen. So then it says tell why there's no value within the interval where g prime of c equals the slope of the secant line. What does g prime represent? It's our derivative, but what does the derivative represent? Slope of the tangent line. So this is just another way of saying the slope of the tangent line is the same as the slope of the secant, which just means they're parallel. So that's just another way of saying it. So some of you might have said, well, because it's not differentiable at a point, you might have said something about the slopes are steeper. I would probably stick with that. So that's what I'm going to put down. My slopes, if we look at all my little tangent slopes here, they're all steeper than the actual secant slope itself. So the slopes of the tangent lines are steeper than the slope of the secant line. Not looking for any earth-shattering mathematical discovery here. Just kind of your explanation as to why it's never the same. You could have said that the slopes of your tangent line are never the same value as that secant line, or whatever you want for that. So this is interesting because for the first time we've seen that it did not meet one of these conditions. It was continuous, but it was not differentiable. And interestingly, we don't have a tangent line parallel. All right, so let's take a look at 4. Same graph, different interval. All right, so we're looking on the interval 1 to 4. So my height at 1, my height at 4. And if I draw on my secant, I didn't do as good on that one. And it says there actually is a time in which we have that parallel tangent line. And I think about here, that was good. Let me try again. This one I feel like is the hardest. Alright, we're just going to go with it. So we do actually have a time along here in which my little tangent lines, the slopes of those tangent lines, one of them is parallel to the secant line. Alright, so where approximately did that occur? Was it like 2.5 or 3-ish? I think it might go 2.5. Somewhere around there. Alright, is my function differentiable on the open interval here? Yeah, because if I take a look, the piece of my graph that I'm interested in, I can take a derivative everywhere along there. I can draw in little tangent slopes everywhere along there. We don't have a cusp because we don't continue beyond there. So I can draw the little slopes leading right up to it. We don't include 4. We do not have the derivative 4. And if we notice, my interval does not include it. So it does not mess us up there. 4 is not a part of my interval, so we do have it as differentiable on it. Is it continuous on the closed? So now we're back to being differentiable on the open, continuous on the closed, and lo and behold, we have a tangent line that is true. All right, questions on the front side. So now on the back side, they give us a piecewise function. And again, thankfully, they've graphed it for us. So it says draw secant line through the point 5 in its height and 7 in its height. So double check to make sure you had the secant line correct here. The point 5, h of 5, is the filled in dot up here. It is not that open one, because my function is not defined at this height, but rather the higher height here. And then 7, h of 7. So my secant line is going to be that. So if you drew it using that open circle, go ahead and erase that and fix it there. So then we have to use the closed dot, because that's where the function is defined. Is my function differentiable on the open interval 5 to 7? Give me thumbs up for yes, thumbs down for no. Is it differentiable on the open interval? See some mixed answers. I'm going to go with yes. Because it does not include 5, right? So I'm looking only at this open interval here. Again, since it doesn't include 5, we don't care what's happening at those endpoints. So 5, there is an issue. It's not continuous, so it can't be differentiable. But since 5 is not included, we're good. Leading right up until I can take the derivative. I can draw those tangent slopes. So that it is actually differentiable on that open interval. Now, is it continuous on the closed interval? No. So it is not continuous on the closed because it does include the value 5, and at 5 we have to start here and jump down to continue on. So it's not continuous on the closed. Alright, So here, why is there no value in that interval for where the tangent and the secant slopes are the same? Again, you could have said a variety of things. What I'm noticing here is that my secant line is a negative slope, whereas all these little tangent lines are positive, so I'm going to go with that. Secant slope is negative, tangent slopes are positive.
Is there any correspondence between their naming secant and tangent that we could connect some other math?
In geometry, that's what it was defined as, a tangent. So in geometry, a tangent line was what hit the circle, that's that example, only at one point. So it's just what it's defined as. It's a vocab word from geometry. So that's a tangent line where it hits it at the one point. The secant is where it hits it at 2 points. So it's the same phraseology as geometry. Just now we're not looking at it in circles, but in terms of a graph. Does that make sense?
Yeah, what about trigonometry?
I don't think so. But I can look into that for you. But I have not heard of a connection. Alright. So again, here we have a piecewise. Notice that it failed one of my conditions of differentiable and continuous. This time it failed continuity. But notice it did fail it, and we didn't have a parallel tangent line. Alright. Let's go take a look at the one below it. Same piecewise graph, but now we're looking at the interval 5 to 9. And here's 9. Drawing in my secant line. Alright, is H differentiable on the open interval 5 to 9? Indeed, we don't have to include 5, so we're not worried about what's happening at the endpoint here. Is it continuous on the closed interval 5 to 9? No. But interestingly, there is actually a point where this tangent line is parallel to the secant line. And let's see where that goes. Got down here. Somewhere around 5.5, 5.7-ish. I'm going to go and say 5.5. So here we have it failed one of my conditions, yet we did happen to have a tangent line parallel to that secant line. Alright, and then finally our last graph, number 7. So same graph, different interval. Now we're looking on the interval 1 to 5. And if I draw my secant line here, it says that there is a point within this interval where that tangent slope is the same as the secant slope. So drawing that in, somewhere around here. Is my function differentiable on the open interval 1 to 5? Yeah. We're looking again just at this branch of our graph here. And we don't care what's happening at the endpoints, but we don't have to jump around anywhere at all. So yep, it is indeed differentiable. And then it says explain why it is continuous, even though there's a step discontinuity or jump discontinuity at 5. So why is my function considered continuous on the closed interval, even though we have that jump there? Yeah. If you would, I'm going to call this a branch of my graph or a piece of my graph, because it's a piecewise function. This blue piece, that interval 1 to 5, 5 is included on that branch that we're talking about. So it doesn't require us to jump around at all. We would only have to jump if we were going right past that 5. So let's see. The interval 1 to 5, both contained, is on a single branch of the graph. And what I mean by that is it's all in that same piece. So it doesn't cause any issue for us. Again, 5 is included on the interval, and we can see 5 is included on that branch of the graph where the rest of our interval lies. The entire interval lies in the same place. Alright, questions on our graphs 5 through 7. Okay, show me thumbs up, thumbs middle, thumbs down how you did with this now that we've gone over it. Good. Okay, so now let's take it home. with actually looking at the mean value theorem. So the mean value theorem states that if f is differentiable on the open interval and f is continuous on the closed, so these are the two conditions that must be met. Differentiable on the open, continuous on the closed. Then there must be a number in that interval, somewhere within that interval, such that f prime of that value is equal to the secant slope there. So this, again, it's my derivative, which represents the slope of the tangent line, is equal to the slope of the secant on that interval. And again, our slope of that tangent is just the derivative. The slope of the secant, that's just our algebra 1 slope. Now, I'm going to use an acronym that I learned from the coworker as to help us remember this. The big idea is that IROC equals AROC. And let's write out what those are. So IROC is instantaneous rate of change. And what's the calculus word for instantaneous rate of change? Derivative. So this is just our derivative, which again is the slope of the tangent line. Alright, so we're saying our instantaneous rate of change, the derivative, is equal to, what do you guys think AROC stands for? Average rate of change. Average rate of change. And my average rate of change is just that algebra 1 slope, or in other words, the slope of the secant line. So the mean value theorem says for any function that is differentiable on the open and continuous on the closed, automatically guaranteed that at some point in time in that interval, our IROC, the instantaneous rate of change, will equal AROC, our average rate of change. The derivative will equal that algebra 1 slope. It could happen more than once, like we saw in one of our problems, but guaranteed it will happen at least once. If it does not meet these conditions, then we don't know for sure. It could possibly still happen, but we don't have that guarantee. So the mean value theorem is what we call an existence theorem, meaning that if it meets those conditions, there exists some number in that interval that has that property where the instantaneous equals your average. Alright, so now that we've gone through and double checked our answers for these, I want you to go back and figure out which problems did we have both the hypothesis and the conclusion true. Where it was differential, it was continuous, and we had that tangent line. And then figure out where the hypothesis and conclusion were not true, and then the one problem where we had the tangent line even though it wasn't differential and continuous. So take just about 30 seconds, go through and classify each of those 7 problems in one of those categories. So which problems were both the hypothesis and conclusion true? Where we had differential, we had continuous, and we had the tangent line parallel. Which ones did we have for that? I heard 1 and 2. 4, and 7. Do we agree with that? We should see yes, yes, pair. All right. Which ones did we have the hypothesis and conclusion not true? Where it failed either differentiability or it failed continuity, and thus we didn't have a tangent line. 3 and 5. Okay. And then what was the single problem where it did have a parallel line even though it failed one of the conditions? 6. That's our buddy over here. All right, so what number 9 is saying is, it says the hypotheses are sufficient conditions but not necessary. So what that's saying is that if those conditions have been met, differentiable on the open, continuous on the closed, we are guaranteed by the mean value theorem that IROC equals AROC. That doesn't necessarily mean it can't go backwards. It doesn't mean that just because we have the tangent line parallel that it satisfies those conditions. But it could be that even though it fails those conditions, it does have a parallel line. So in order for this to happen, we don't have to have that it's both differentiable and continuous. It could happen without meeting the original conditions. But we know that differentiable and continuous automatically guarantees that that will occur. Okay? So if our conditions have been met, when those hypotheses, differentiable and continuous, have been met, so when the hypothesis has been met, or hypotheses are met, then IROC equal to AROC is guaranteed. It must happen. That doesn't mean it can't happen other times, but we just don't know for sure. Here, though, if it meets differentiable and continuous, we know for sure, without a shadow of a doubt, that we will have the instantaneous equals the average at some point. All right, questions with that? So mean value theorem is kind of the big idea for today. We're going to recap IVT, intermediate value theorem with it. We're going to take a look at a special case of mean value theorem called rolls, but this is the big takeaway, a pretty big concept in calculus, and we're going to do some problems that shows how mean value theorem can kind of sneak in unnoticed. But before we do that, let's go ahead and recap what we know about IVT and take a look at rolls. So just get a blank sheet of paper, and we'll do kind of a little bit of review / a little bit more information. Yeah, this is pretty wonderful. Not even let Alright, so intermediate value theorem we learned earlier in the year, but I think it was like September, October, so it's been a little while. Let's refresh our memories with it. Can you guys think of another word for intermediate? Kind of like in the middle somewhere, right? In fact, middle school used to be called intermediate school back in the day, before my time, but a little while ago. So intermediate value theorem is basically saying that as long as the conditions are met, it's continuous and the endpoints are different values, then the middle stuff is guaranteed. Whatever values that occur in the middle are going to have a y value with it. So let's just go ahead and formally write it out to refresh our memories, and then we'll take a look at the value theorem. So intermediate value theorem, a continuous function and we'll go with old reliable f of x. A continuous function on the interval a to b, closed interval a to b. And our endpoints are different heights, so f of a does not equal f of b. Okay, so continuous function on the closed interval where endpoint heights are different, must have a value C, must have a value C such that C falls within that interval, so A is less than C, which is less than B. And the big idea that its Y value is somewhere between the endpoint Y values as well. So f of A is less than f of C, which is less than f of B. So a continuous function on the closed interval where the endpoint heights are different must have some value in the interval where its Y value is contained between the endpoint Y values. So basically what this is saying is that every Y value within this interval will have an X value within its interval as well. Now I do want you to put a little asterisk next to this end piece here, because it could be that perhaps B has the higher height, and that's fine. So it could be that f of B is less than f of C, which is less than f of A. The idea, though, is that the height for C is contained between those endpoint heights. So as long as my function is continuous and the endpoints are different heights, then all that middle stuff is guaranteed. Kind of like if you went to school continuously, you didn't skip any grades or randomly drop out in elementary school for a while. Assuming you went to school continuously from kindergarten to 11th grade, then I can assume that you hit every single grade in between. Again, if you think about continuous function, must hit all those values. Alright, so that's our intermediate value theorem. That's what we did earlier in the year. Now, our mean value theorem or MVT is similar to intermediate in that it requires the function to be continuous. If we look at our intermediate value theorem, it had to be continuous with endpoints different heights. For mean value theorem, our function must be continuous, but also it has to be different. Yes?
Was the intermediate value theorem the one abbreviation we were allowed to use?
Yes, so IVT and MVT is accepted. MVT is an appropriate abbreviation on the AP exam. Whew, lock that one in your book. IVT, MVT, FGC, that's it. Unfortunately. So mean value theorem, again, you want to think, you want to think the big idea is I rock is equal to A rock. That's kind of the big concept for mean value. But we have to meet certain conditions first. So our mean value theorem says if f of x is continuous on the closed interval, A to B. So similar to intermediate, it has to be continuous on the closed, but it also has to be differentiable. So and differentiable on the open interval, A to B. So continuous on the closed, differentiable on the open. So for any function that meets those two requirements, then it must follow what we're about to write. So if f of x is continuous on the closed and differentiable on the open, then there exists a value c such that, once again, C falls within that open interval, such that A is less than C, which is less than B. So again, similar to intermediate, it falls within the interval, and the special property for mean value is that f prime of C is equal to f of B minus f of A over B minus A. So it's similar to intermediate in that it requires it to be continuous, and our C value is contained within the interval. But intermediate value theorem said our C is contained in the interval and the Y value is contained within that interval. Whereas for mean value, it must be also differentiable, and the big idea is that the derivative at that point is equal to the secant slope at some point. So again, what we have here is this is my instantaneous rate of change, I rock. And on the right here, it's my average rate of change, A rock. And again, instantaneous rate of change, it's just your derivative. Average rate of change, that's your algebra 1 slope. And so sometimes we'll have problems where they actually give us the function, we can find the derivative, but sometimes they'll give us problems where we only have a chart of values, and we actually have to use the algebra 1 slope to help us solve it. Alright, so intermediate value, as long as it's continuous with different endpoints, then there's a value somewhere within the interval for the Y value within its interval. Mean value theorem, as long as it is continuous on the closed and differential on the open, and there's some value within its interval, so somewhere within the interval, that derivative, the slope of the tangent line, instantaneous rate of change, is equal to the slope of the secant line, or your average rate of change. So again, this is slope of tangent. That's what the derivative represents. And this is the slope of the secant. Now your function must be continuous and must be differentiable in order to meet this. If it does not meet that, then we cannot guarantee that they will be the same. It might happen, but we can't guarantee. Alright, so interestingly, mean value theorem is actually used quite a bit dealing with traffic and recreating accident scenes sometimes. And the Massachusetts Turnpike actually used to use the mean value theorem a while ago to issue people tickets. We'll talk about that more in just a moment. We're going to do an example that kind of lets you see how it's used with traffic. Alright. And remember, mean value theorem, it can give you more than one time at which these values are the same, but guaranteed at least one. Alright, so let's check out this example. Alright, you are driving 50 miles per hour, an innocent speed. You're driving 50 miles per hour on a straight highway. And you pass a cop with a radar gun. So this is a straight highway with no stoplights, so a smooth and connected curve. And what does 99% of everyone do when they see a cop? Slow down. Whether you're speeding or not, that seems to be the instinct. Alright, so you're driving along on the highway, and when you pass a cop with a radar gun, you're going 50 miles per hour. So we're on highway, it's okay, you weren't speeding. Then 4 minutes later, you pass another cop with a radar gun. They're sneaky sometimes. Alright, so 4 minutes later you pass another cop with a radar gun. And again, you're still traveling, or at this point you're traveling 50 miles per hour. So while going 50 miles per hour. Two innocent situations, two innocent scenarios. Cop 1 sees you, you're only going 50 miles per hour. 4 minutes later, you get to cop 2. You're only going 50 miles per hour. And the 2 police are 5 miles apart. Hello. The 2 police are 4 miles apart. What did I say? Sorry, 5 miles apart. Are 5 miles. Alright, still sounds innocent, right? We haven't done anything wrong. But then the second cop gives you a speeding ticket. And not only does he give you a speeding ticket, but he gives you a speeding ticket for going 75 miles per hour. Wow. And guess what? If you went to court, you would win. Yes. Let's go with 55. What is it on Fairfax County? Is it 50?
Yeah.
Okay, we'll go 50. We'll go 50.
And you only 5 miles.
Well, take another brisk walk and see if they need you again. Alright, so it seems like we've done nothing wrong, right? At cop 1, we're going 50 miles per hour. And then cop 2, we're going 50 miles per hour. But he seems to think that at some point we were going 75 miles per hour. Why? Well, let's take a look at this and see. So my position when I pass the first cop, we'll say is 0. So let's let that be our starting point. Our first cop, we're going to say time 0, position 0. We're starting from that point. Then when we hit the second cop, how far have we traveled? 5 miles. And our speed is measured in miles per hour. We know it was 4 minutes later, but let's keep it all in the same unit. Since it's miles per hour, let's go and convert. What's 4 minutes in terms of hours? 4 over 60, which is? 2 over 30, which is? 115. Good. Alright, so at time 0, we are at position 0 with our first cop. And then 1/15 of an hour later, we have traveled 5 miles. Alright, so let's go ahead and calculate our speed over that time frame. Nope. Okay. Okay. So my speed, or my average rate of change, is going to be 5 minus 0 over 1/15 minus 0. Now think about what we just did here. This is my average rate of change. These are my endpoints of position. If I am doing the average rate of change of position, so change in position, change, okay, change in position over change in time, what does that give me? Velocity, yeah. Or if you think about it, my position is miles, right? We're doing change in miles over change in time, miles per hour. So this is going to give me my velocity in miles per hour. So my average rate of change of position is velocity, just like the instantaneous rate of change of position is velocity. So this would be velocity as well. So what we're finding here is actually our speed. So 5 miles over 1/15 hours, what does that become? 75 miles per hour. Yikes, he was right. So since this is a smooth and connected curve, straight highway without any stops, it is continuous and differentiable. So by the mean value theorem, the mean value theorem says that my instantaneous rate of change is equal to my average rate of change at some point in time. So if my average rate of change was 75 miles per hour, then at some point in time I must have been going 75 miles per hour. So because he knew how long we had traveled, or how far we had traveled in such a short amount of time, we must have at some point in time hit 75 miles per hour. And thus, he rightfully can give us the ticket there. Now, of course, he has to know calculus to defend it in court, but perhaps this is a very smart cop that he does. So that is why he is able to know that we did go 75 miles per hour at some point in time. We probably went more than one point in time, but guaranteed we had hit it there. And again, the big idea is that this is the key thing. We went pretty far in a short amount of time, so we must have gone fast in speed. So this is how it kind of connected with the Massachusetts Turnpike. And I heard this from another coworker. But what she said was that, so the Massachusetts Turnpike had toll booths. So you drive, you get onto the toll booth, you get a little ticket thing that says what toll booth you entered in on and what time. And you drive. And when you go to get off the turnpike, it stamps it again with the time and the toll booth. So what they were doing is they knew how far that distance was. And they knew that traveling the speed limit, how long it should have taken to travel that. And people that were coming through and their timestamp was quicker meant that they must have been speeding at some point in time. And they could use this to help them figure out, okay, how fast were they going, and then they would mail them home a nice little speeding ticket into the mail. This was taken to court in Massachusetts, and the people won something about privacy of toll booth ticket or something, expectation, I'm not sure. But it was no longer allowed. But I thought that was really interesting. That was pretty smart, though, pretty sneaky. You think you're just cruising along the toll booth, and then a week or two later you get a speeding ticket because you went too fast. And they knew it using calculus. It's everywhere. Okay, so this is an example of how mean value theorem is used with traffic law, with the accident reconstruction. So if there are traffic cams nearby, and they are able to see the car at one point in time, and then how much later down the road, another point in time, they can figure out that they must have hit a certain speed if they were speeding in that time frame. So sometimes they use it for that as well. Okay, so our last piece before we do some practice problems is called Rolle's theorem. And Rolle's theorem is actually just a specific case of the mean value theorem. So it's still mean value theorem, we're just looking at one specific version of it. Just like with intermediate value theorem, we looked at the specific case where it guaranteed that it crossed zero. We knew if it went from positive to negative, the y value must have been zero at some point in time. Similar thing for Rolle's theorem. So since this is just mean value theorem, it still has the same requirements of being continuous and differentiable. So if f of x is continuous on the closed interval a to b and differentiable on the open interval a to b. Okay, so it's still mean value theorem, just a special case, or specific case, so we still have the same requirements. Continuous on the closed, differentiable on the open. Alright, now the specific case is when our endpoints are actually the same height. Okay, so if it's continuous and differentiable, and we have the specific case where f of a equals f of b. Okay, so that's kind of the new piece there. I'm going to underline that. Then there exists a value c such that C is within the interval just like before. And then here's the kicker with it. So if my endpoints are the same, then Rolle's theorem lets us know that at some point in time, my derivative is 0. Alright, so again, it's still mean value theorem in that it's continuous and differentiable, and the value C must be within our interval there. What's different with the specific cases is that when my endpoints are the same, then that means at some point in time, my instantaneous rate of change will be 0. My average rate of change will be 0. So let's stop and think about this, because it's kind of an obvious. So if I have two values where my heights are the same, I'm going to call this f of A, which is equal to f of B. Then when I go to do my AROC, my average rate of change here, what is my slope when my heights are the same? 0. And so my AROC must be 0. Also, if we try to draw any continuous differentiable function where these endpoints are the same, no matter what we do, at some point in time, you're going to have a tangent line that is the slope of 0, or you're going to have a derivative that is 0. So, for example, if I go up, I've got to come back down at some point in time. Notice I have a tangent line that has a slope of 0. My derivative at this point is 0. Even if I change it up and went a different direction. Say I went below first. I still have to come back up to that height at some point in time. So again, at some point in time, in between there, I have to have a slope of 0. Even if we did both. Maybe you go crazy. Maybe you're like, look at that. There are multiple times in which you have a slope of 0. And even if you try to be sneaky and say, oh yeah, Mrs. Margraf, well, what if I just did this? What is your slope that entire time? 0. So the idea is that if they're the same heights, you can either go straight across, which is slope of 0, or regardless of whether you go above or below, you're going to have to turn back around to get that height again, and it's going to cause that to be a slope of 0 at the top. So that's the idea there with Rolle's. If our endpoints are the same, then it's guaranteed that at some point in time, my slope will be 0. Questions with that? I realized when we drew this picture that I never had you draw a nice picture for mean value there. So let's draw a picture for that. Even though you did it a million times in exploration. Alright, so mean value theorem, we need to have a continuous and differentiable curve, so draw whatever you like. Starting at A, finishing at B. Here's F of A. Here's F of B. Alright, so for any curve that is continuous and differentiable, there we have an example. Our secant line, we'll draw that in. Is going to be parallel to the tangent line at some point in time. For my curve here, it looks like it occurs over here. And looky there, I even got a second one in. Now, again, it doesn't have to always be 2. It just guarantees at least once. But it guaranteed at least one time within this interval. And I can see it occurring here. I'm going to call this C1. And it occurred here. C2. So it's continuous, it's differentiable. There exists some C value within our interval where the tangent line slope is the same as the secant line. So it means my tangent line and secant line are parallel. Alright, questions with that? Okay, so let's go take a look at some practice problems. Wait, I'm going to throw it back to this side in case you missed any of it. So your homework is going to be to do worksheet 5.1. That's what we're going to go ahead and start working on. Also, a quick reminder that your AP winter review packet, woohoo, is due next class. If you forgot yours, lost yours, I have extra sitting in the tub over here. It's also posted up on Blackboard. But don't forget to complete that for next class. Assuming we are here on Friday. Do you need one more? The AP exam is May 15th. Let me double check that. May 15th. I'm 99% positive on that. We're unfortunately the second week of exams. Alright, is there anyone that did not get worksheet 5.1? It is not. In fact, they're sending out an email about that. I think that's I honestly am not sure. But I have a meeting Tuesday with one. So ask me after that. Alright, so we're going to go and just do some problems that deal with mean value theorem, intermediate value theorem, Rolle's theorem, and you'll notice some problems explicitly state it and some problems don't, and you have to know when to be able to use it. So keep in mind, intermediate value theorem is talking about the stuff that's happening in the middle. Intermediate value theorem is talking about something with the derivative and the secant line. Typically, when it talks about derivative, that's a hint towards mean value. Not always, but it's a hint in that direction. Alright, so let's just take a look at number 1. The function f is continuous and nonlinear. What does nonlinear mean? It's not a line, not a straight line. Alright, so it is continuous and nonlinear for this interval. And they give us some values about the endpoints. If there is no value c in that interval for which the derivative equals -1, which of the following statements must be true? Now, let's go ahead and take a look at what they've given us. We have continuity. Nonlinear just means it's not a straight line, so it moves all around. And if it helps you to visualize it and you want to kind of just sketch the endpoints, that's fine. It's not really necessary. Me personally, I like to do it. So -3, 5, 7, -5. So we know that something's happening in between here. It's not a straight line. We have it's continuous. All right. And then they tell us there is no value c where the derivative equals -1. If that's the case, which must be true? Now, intermediate value theorem is asking for values within the endpoint values. And if I look, my answer choices are all talking about the derivative. It's not talking about my original function. So that's probably going to give us an idea not to use IVT. Now, mean value theorem, we know we have to have continuity and differentiability. Mean value theorem, I must have continuous on the closed, and I must have differentiable on the open. And then I can say that my instantaneous equals Alright, so let's see. Do we have that it's continuous? Yeah, they gave that to us. That was very nice. Do we have it's differentiable? Nope, that seems a little concerning. But we do see that they have something about the derivative being equal to -1. Where's that -1 coming from? Perhaps it's that average rate of change. So they're saying there's no value where the derivative equals -1. Let's just double check to see what our AROC is. Alright, so we have -5 minus 5 over 7 minus -3. So -10 over +10 over -1. Lo and behold, that is what it is. So what they're saying here is there's nowhere on that interval where my instantaneous equals that average rate of change. If it does not hold true, then there must have been a break in the conditions. Because we know that if the conditions are met, it must happen that IROC equals AROC. So if they do not equal each other, then one of these must have failed. Which one must have failed? Differentiability. Because we know it's continuous, so it must have failed differentiability. So that's what we're looking for. If IROC cannot equal AROC, then it must have failed for this particular one, differentiability. So let's take a look at our answer choices. A, for some k in the interval, the derivative is less than -1. We have no information about that. We're just looking that it's not differentiable. Derivative is greater than -1. Again, no information for that. We're just looking for not differentiable. For some time in that interval, the derivative equals 0. Again, we don't know. D, for some time within the interval, the derivative exists. No, that's actually the exact opposite of what we're looking for. We need that the derivative does not exist. So this is a huge no. Alright, E, please let it be. For some k in that interval, the derivative does not exist. And that is our winner. Because again, we have that if it does not meet IROC equal AROC, it must have failed somewhere. We know it had to have failed differentiability because they gave us those conditions. Questions with that one? Notice mean value theorem was not stated anywhere within that problem. So you have to know, you have to be able to recognize when to use it. Alright, let's take a look at number 2. This is a pretty common type of problem. So we've got Mr. iPup, a new robotic dog. He went on sale at 9 and sold out within 8 hours. The number of customers in line to purchase the iPup is modeled by a differentiable function, and values are shown in the table below. For time 0 to 8, what is the fewest number of times at which the derivative could equal 0? So here it's the number of people with hours, so my derivative would be that rate. Now, if I were looking at, let's break this down a little bit. We see that it says it's modeled by a differentiable function. That is a key and very important word for us. If they tell us that our function is differentiable, that automatically means it is also continuous. Differentiability implies continuity. If a function is differentiable, we automatically know that means that it's continuous. So we have that it meets both requirements of differentiable and continuous. All right. So we know we can apply mean value theorem. So mean value theorem says if it's differentiable and continuous, it automatically follows that IROC must equal some point in time. And they're asking us how many times does that happen. Now, can I find my derivative here? Do I have a function of which I can do the derivative? No, they didn't give me a function, so I cannot do the derivative. But they gave me a table of values, so I can certainly find my average rate of change. I can do slope 1,000,000 times over. So let's do it a little less than 1,000,000 times over. All right. Because I know if my average rate of change is 0, then there has to be a point in time in which my instantaneous rate of change is 0. So we're finding out how many times does that happen. All right, so let's go and take a look from 0 to 1. All right, doing my slope here, 185 minus 150 over 1 minus 0. What does that give us for our slope? What did you say?
-4 over.
No, it's nicer than that. 35, right? Okay. So my A rock for this time interval is 35. Okay? Well, let's check it for the time interval 1 to 2. Alright, so now looking from 1 to 2, 135 minus 185 over 2 minus 1. What does that simplify down to? I heard one person say it. Negative 50. Are we good with that so far? Okay. Now we can keep doing this down the line, but let's save ourselves some time. If my average rate of change was 35, and this is a smooth and connected curve, differential and continuous, and then my average rate of change is negative 50, did my average rate of change cross 0 at some point in time? Yeah. So I know that it must have crossed 0 somewhere within this time frame, at least once within there. So are you guys okay if instead of finding the actual value, we just determine positive versus negative? Because that's all we really care is, does it cross 0? All right, so let's go ahead and do that. So 120 minus 135 over 1, is that positive or negative? With 121 minus 135, positive or negative? Negative. Good. Woo. All right, 75 minus 120 over 1? Negative. 75 minus 75 over 1? Oh, look at that, they gave us one. How nice. All right, 100 minus 75? 120 minus 100? Positive. 60 minus 120? Negative. And again, we were checking the slopes for each of those, but I knew that each of them was going to be divided by 1. All right, so let's see how many times we would have that it hits 0 or crosses 0. So we see within here, positive to negative. You can just put a pattern mark. Within here, now they gave us actually the 0, but we know that's another time. And then one more time, right? So we have that it hits 0, my average rate of change hits 0 3 times. So my instantaneous rate of change must hit 0 3 times. And that is hiding behind C. Questions on that one? Now, technically, what did I use when I was comparing that my values went from 35 to negative 50, thus meaning it crossed 0? Yeah, we were technically using intermediate value theorem with that. So we technically use intermediate value theorem and mean value theorem. Okay. Questions on that one? Okay. Let's take a look. I think I want to do next. No, I take it back. I want you to turn, I think it's number 11. Yeah, let's go to number 11. So number 11 says let f be the function given by x cubed minus 3x squared. Pretty innocent function. What are all values of c that satisfy the conclusion of the mean value theorem of differential calculus on the closed interval 0 to 3? All right, so all that's saying is, hey, I want to know exactly where that tangent line is parallel to the secant line. So we know from our mean value theorem that if it is continuous and differentiable, then my instantaneous rate of change must equal my average rate of change. So what they want to know is when does that occur? What is the x value, that c value for which that occurs? All right, so what we need to find is first our derivative and our average rate of change. All right, what is my derivative going to be? 3x squared minus 6x. Do we remember derivatives? I know last year was a long time ago. All right, so that's my derivative, and I want to find when does that equal the average rate of change. Remember, average rate of change is just my algebra 1 slope. So for this particular one, it'd be f of 3 minus f of 0 over 3 minus 0. Are we good with what I'm doing here? Okay. So we need to actually find f of 3 and f of 0.
Good afternoon, Curtis. Please pardon this interruption. Boys soccer green day practices start today as scheduled.
Thank you, and have a great afternoon. Alright, so f of 3 is 3 cubed minus 3 times 3 squared. And then f of 0 would be 0 cubed minus 3 times 0 squared. Alright, what do we get for this first one? 0, yeah, because 3 times 3 squared is just 3 cubed. What do I get for this guy? Oh, well, that's interesting. So what's my slope going to be? 0. Okay, so we want to solve and find what values of c satisfy this. So let's bring it together. Let's go back to my original piece here. Alright, so I want to know, when does my derivative, 3x squared minus 6x, equal my average rate of change, which we just said was 0. You guys know how to solve that? Just factor, go from there. 3x times x equals 2 equals 0. X equals 0, x equals 2. That's interesting because we got 2 choices, and those 2 choices aren't paired up together in our answer choices. Comes back to technicality. If I take a look at my mean value theorem, can my c be one of the endpoints? No. My c cannot be one of the endpoints. It's not included. So what's my answer going to be? 2. Ding, 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 ding. And, oh, look, we did it right. The answer is right there. The answer key for this with the work is up on Blackboard, but you'll notice some of the multiple choice questions you have to use. All right, so your homework is to finish worksheet 5.1, and don't forget to bring your completed review packet next class. It will be a grade for correctness of some sort.